Hello, my name is Diana Diaz and I will be presenting a study on weight reduction by numerical simulation for a lightweight MuCell injected component. First, I will talk a bit about the research center I belong to. I work in PIEP, which is a private association based in Portugal, and our main focus is innovation in polymer engineering. We have several areas of expertise, and we do test and failure analysis, product design and development, advanced manufacturing for either composites and polymer materials, extrusion compounding, and research on advanced materials, and circular economy. The study I bring to you today is based on the EDPMU project. EDPMU is a consortium project that has as main goal the integration of different technologies for injection molding. In this case, specifically overmolding, in-mold labeling, in-mold electronics, and microcellular injection molding, in this case MuCell, are integrated into a one-step process to reduce injection cycles and produce lightweight products. The study here I bring to you today is going to be focusing on the MuCell injected part. In this case, for microcellular injection molding, with physical bonding agents. The study and the model in the study is presented here on the right side of the slide, and we proceeded with two different phases along the study. So the first phase was to determine which was the most suitable gas for this specific part, as it is a component developed for the automotive industry. We must have some considerations with its cellular structure, because microcellular injection molding is known to produce components with reduced mechanical properties. So we needed to make sure that the density and cell structure throughout the part is uniform. In the next phase, and having decided which gas we're going to go on with, we studied the most influent parameters on microcellular injection molding to determine which were the parameters we needed to optimize to obtain higher weight reductions. So in the first case, with case study with nitrogen versus carbon dioxide, we started the study with different amounts of incorporation, either for CO2 or N2. We wanted to determine which was going to be better for this part. So we evaluated weight reduction, cell density, and cell size. Weight reduction would give us which gas was better to obtain higher amounts of weight reduction, and cell size and cell density, which would help us predict which was the better cell structure for this part. So what we wanted to do was to analyze different amounts of incorporation of either N2 or CO2 and evaluate these results. The amount of incorporation of CO2 and N2 is very different because either gases have very different values of solubility in the polymer melt. In the case of CO2, it is much more soluble, and so to saturate the melt with the gas, you need a much higher quantity of CO2 than N2 for the same result. So by analyzing the results we had, we could see that weight reduction was not a very variable factor, a response that we could actually vary. And it is important to note that in this phase, there is not an injection molding equipment, so a lot of the process is still being defined, so there is not an optimization. So weight reduction here values are still low. And we have to center our study in the cell size and cell density. So what we could analyze and could define was that the cell density was higher for nitrogen than for carbon dioxide, with lower cell sizes. And what means to have higher cell density and lower cell sizes is that for the same region, for the same cubic centimeter, you have a higher number of cells with lower size, so it means that there is lower quantity of empty space due to the gas, and the mechanical properties would be higher. So in this case, we chose carbon dioxide to continue with the study. Having chosen the carbon dioxide, we then went on to perform a DoE Tagushi L16 matrix to determine which of the most influent parameters were to obtain high weight reduction. In this case, the input factors were determined by an extensive literature review, and as we wanted to know specifically for this part which was the best results, we conducted this DoE with these four factors. So the factors were filling time, gas incorporation, melt temperature, and velocity point switchover. In this case, the velocity point switchover is the amount of material that is on the cavity. So we wanted to have a 95% fill or a 98% fill of the cavity before finishing the filling of the part. Once again, the evaluated responses were cell size, cell density, and weight reduction. In this case, weight reduction is the most important. However, we have to analyze also cell size and cell density because we want to make sure that the cell structure is good for the produced part and to promote good mechanical properties. Having conducted this DoE, we then study the most influent parameters as a result of the responses we obtained. The responses are presented here on the table on the right, and we, from the graphs, from the influence graphs, we can see that for cell size and cell density, we will have inverse responses, which is for higher cell sizes or lower cell sizes, that is what we want, lower cell sizes, we would have to incorporate 0.5 amount of the gas, which is one of the most influent parameters, and fill the cavity to 98% with the velocity point switchover, which is another of the most influent parameters. In the case of cell density, we want to have higher volume of cell density. So again, we can see that the 0.5% of gas is the most is the best result for this part, and again 98% of the fill cavity promotes also higher density for the part. But when analyzing weight reduction, we can see that the influent parameters change a bit. So what we can analyze is that the filling time is one of the most influent parameters, along with the VP switchover. It's also another very important parameter. So here what we can see is that for 95% of filling cavity, it's better to achieve high results for weight reduction, which makes sense because we're filling the cavity with lower amount of material and letting the gas expansion to fill out the rest. However, we can see that if we do this, we will have lower cell density and lower cell size. So this is why it is important also always to analyze these three results together, because we have always to have in consideration, because in 95% we will have near the weld lines, probably the cell size will be bigger than it is near the gates, and we will have different mechanical properties throughout the part. Then we wanted to analyze this part. In this phase, we already had the possibility to inject some parts, inject some components. So we did this study and wanted to correlate this simulation with the experimental setup. What we did then some injection of some parts, and we analyzed the run number 4, in which we could see that the weight reduction is very similar to injected part, predicted and to injected part. And in the other cases, it is very similar. However, for run number 11, we could see that we have a bit of change here. We have almost 3% of variation, which is not very high for this part because the part weighs 100 grams, and so 3% is not a lot. However, we wanted to evaluate why this variation occurred in this case specifically, and we did the correlation analysis in this part. We then analyzed the microcellular structure of the run number 11 and did the analysis in three different sections. Number one, which is a region that is neither too far from the gate, and not near the well lines. Number two, which is near the well lines, and number three, which is near the gate. So expected to have different cell density throughout the part and different cell sizes, specifically because we have different regions being analyzed. However, and we can see some degree of that. Analyzing this and comparing the results with a numerical simulation, we focused on the cell size of the part, the shell thickness to evaluate if the simulation could in fact evaluate the shell thickness, and the density. In this case, the cell density is not as visual, and the results that we obtain are very uniform. So we went on and analyzed the density because we know that the density is a thing that varies along a microcellular injected part. But we could see was that the size of the cells is very uniform throughout the numerical simulation. However, in the real setup, it varies a lot. Specifically here for this image, we have cells that go to 400 microns, and in the numerical simulation, the highest is 138 micrometers. The shell, it could not be clearly seen for the cell size. However, when we go on to the density of the part, we can clearly see some differences. We can clearly see a tendency of the results. Here we can see that the shell has a higher density of material, and when you go on to the core, you have lower densities of material, and so you can conclude that there is a formation of some kind of cell structure throughout the part. And if that density varies, you can conclude that the density varies. However, it cannot still accurately predict the variation of density throughout the part. So we wanted to confirm this analysis, and we went on to another section of the part. And in this case, what we could see was that the shell, in the case of cell size, it's higher. The simulation can, in fact, replicate that there will be a higher shell in this section, and it can also create a tendency in the density of the part. However, for the cell sizes, once again, it could not at all replicate. It is uniform throughout the core of the part, which is not the case for the experiments we had. And finally, we went on to a final section of the part from the analysis I showed before, and this is very interesting because we can clearly see different densities in the cell in the part. What we can see is that even for the shell in the lower section, we have some creation of cells in this shell, and it is replicated in the simulation. We can see the creation, the lower density in this case than the others I showed before. Once again, the cell size could not at all replicate the real setup. Okay, so the shell I mean, in this case, not even the shell could be replicated in the cell size. It is very different from the real setups. However, we can see that there is a creation of some cells in the numerical simulation, and that there is some cells in the real setup, and so maybe that's why the simulation could not replicate it as well, but it is not certain. So from our study, it was possible to um, select the gas, help select which gas was better for our part without having the necessity to produce this part and evaluate each part and characterize and do some tests to determine which gas was going to be better for us. And again, for increasing weight reduction, we could see that the best result was the velocity point switchover. However, we could also see that we have to carefully analyze these results with cell size and cell density. We can see that numerical simulation can closely predict the process for weight reduction, but it cannot yet predict the cell size, but the density can be an indicator. So I think it was a good conclusion from this study. And this was it. I hope you enjoyed this presentation. Thank you.